Hey guys, this is a short video, basically introducing Newton's universal law of gravity. Now, true story. The year it was 1665 was the year in London. It's actually known because there was a great plague in London, and basically the entire city was in quarantine. Isaac Newton was quarantined for 1 year, and it was that year, 1665, where he invented calculus, put forth the three laws of motion, and in the same publication, it gave us universal gravitation. So, yeah, look it up if you don't believe me. It's true. This is, again, very brief, and basically, I don't know if the story of Newton sitting outside under an apple tree and an apple hit him in the head and he discovered gravity is true or not, but here we have a theory of gravity, which, of course, Einstein had to tweak, but still quite, for all intents and purposes, accurate to describe, say, what's going on in our solar system. And that's where we are right now in this unit. We're moving over to the gravity stuff, and then looking at, we'll bring back the circular motion stuff when we look at the motion of satellites and planets. So basically, in words, basically, Newton said that every object attracts every other object with this force of gravity, infinite in range, and it's an attractive force. And I'll give you the formula. It's on your formula sheet. It's not a derivation. It's an assumption about the behavior of the universe. Basically, two masses. Force of gravity between them Now, you may have been used to, if you remember this formula being introduced in Physics 11, the symbol D may have been used for the distance between them. Generally, we use R, and we move over to R, especially in the context of circular motion. But basically, two masses separated by a distance R, masses M1, M2, and the strength of the gravitational force between is given by the formula big G M1 M2 over R squared. So it's an inverse square variation. So as the distance increases, the force drops off inversely with the square of R. That quantity big G is called the gravitational constant. Now, I'm going to also post some lesson notes on this material. So what you're getting today is really just a little snippet. So in order for the equation, for the units in the equation to make sense, and we come out newtons at the end, these are these big ugly units for the gravitational constant. A tiny, tiny number. Okay, the exponent there is 10 to the minus 11. And it's because of that we don't really notice the force of gravity, say, between two smaller objects on Earth, like two cars or two people, etc. It exists, it's non-zero, but it's very, very small. So this is it, really, in terms of the theory, but it certainly is going to be a little more than what you saw in Physics 11. when again, in the context of planetary motion, well, this force of gravity, this is going to be the force responsible that drives the circular motion. And yes, it's not, planetary motion isn't exactly circular. It's actually elliptical, but it's very close, and we can approximate the motion as circular motion with a centripetal force acting on a satellite or a planet given by the force of gravity. First thing to be mindful of is there's going to be some really large numbers to deal with when we start talking about like the mass of the Earth or the Sun or the Moon. This gravitational constant, very tiny number. This is it's going to be an exercise in practicing your calculator skills somewhat. So let's just calculate, say, the force of the weight of a person using universal gravitation. Okay, so 60. Let's say a 60 kilogram person. On the surface of the Earth. So here we go. Suppose I have, and of course this diagram is not drawn to scale. Imagine this is the radius of the Earth. Now, we would never use universal gravitation to calculate the weight of a person, the force of gravity, if we knew the value of the field that they're in. We would just go to what we've been doing since you've learned about weight in a physics class. We have, for a constant gravitational field, we would just go weight equals mg and we get a 588 Newton force. But where we're going to move to is problems where we are away from the surface of the Earth. Now, but again, we could, so you're also going to really need access to your formula sheet or some planetary data, some information here about the Earth. So this is the radius of the Earth, and we also know the mass of the Earth to three significant figures. It's a big number, 5.98 times 10 to the 24 kilograms. And so again, big G, the gravitational constant, is on the formula sheet, the mass of the Earth, the radius of the Earth, and we could find the force of gravity this way. We could actually plug it into universal gravitation. Now, as I mentioned, this is an exercise in practicing the calculator. Really, there's going to be lots of these problems with really big, ugly scientific notation numbers. So try it. Get your calculator out. Make sure you can do this. Okay, and you know where the buttons are that you need to access. And when you do that, you should come out with a force of gravity equal to 588 newtons. So that's about 10 minutes. That's about as long as I want the video to go. So I'm going to stop it there. We are going to move, like I said, we're not going to spend a lot of time on practicing the formula per se. We will get lots of practice in the context of a more formal look at gravity. We're going to be looking at the definition of a gravitational field, and we'll also be looking at gravitational potential energy away from the surface of the Earth. So you can't use the formula mgh anymore because the value of g is changing. So like I said, the next bit will be, let's look at how this gravitational field changes, say at far away from the Earth, from the surface. Okay, that's all I have for you for now. So take care. Bye.